Okay, so yesterday we started talking about these reactions where alcohols are getting oxidized. We talked about how the basic idea of oxidation and reduction reactions is that somebody is losing electrons and somebody is gaining electrons. Always both things have to happen, which is why it's commonly called redox reactions, because if somebody's losing, somebody else has to be gaining. Sort of conservation of electrons, I guess. But it's also, it was originally called oxidation because when people are studying it, they were looking at it in terms of gaining oxygens or gaining bonds to oxygen, which is a good way to think about the oxidation of these alcohols, because that's what's happening, is our carbons are losing hydrogens and gaining oxygens in this process. So we talked about how typically have a few different oxidizing agents that we can use to get these reactions going. A common one that you probably need to know about the color change is the dichromate ion. In this case, our dichromate is going to lose some oxygens. The chromium is going to go from a +6 oxidation state to a +3 oxidation state. Those oxygens are going to get in complete oxidation, where you'll see in a second, some of those are going to get lost to the alcohol. But what's happening here is we have this alcohol, we have this hydroxyl group. The carbon attached to it is basically going to gain an additional bond to the oxygen while losing a hydrogen. Okay? And so that's hence the oxidation aspect of it. It's gaining oxygen, it's gaining bonds to oxygen. Now, primary alcohols that are at the end of the chain can undergo two kinds of oxidation. Partial oxidation, where only one of the hydrogens on the carbon are lost, and we're gaining one bond to an oxygen. It's the oxygen that's already there. This makes an aldehyde. So rather than having COH, we have C double bond O. All right, and then the other hydrogen is just kind of hanging out here. Okay. So primary alcohols can undergo basically like one step of oxidation, what's called partial oxidation, to make an aldehyde. Now, if we continue to keep this reaction going with all of the stuff in the reaction vessel, then what's going to happen is we're going to get what's called complete oxidation. And we're going to turn that into a carboxylic acid. So we're basically adding an oxygen, an additional oxygen onto that carbon. Okay, so instead of C double bond O with an H, we now have OH. We have a hydroxyl group here. So we're now making a carboxylic acid. So that's two additional bonds to oxygens that the carbon has. So that's considered complete oxidation. This is only going to happen when we're at the end of the chain, when the alcohol is at the end of the carbon chain. Okay? And this is also going to take a good amount of our oxidizing agent to make sure that it goes to completion. Now, if we have our alcohol in the secondary position, that carbon only really has one hydrogen to lose, okay? So we're only going to get one step of oxidation to make a ketone. So we're losing the hydrogen and gaining a double bond to the oxygen. It's not going to break the carbon-carbon bonds. Okay, all we're doing is replacing a hydrogen with an additional oxygen bond. So secondary alcohols can only turn into ketones, but primary alcohols can either be aldehydes for partial or carboxylic acids for full oxidation. In any case where we are using the dichromate for oxidation, you're going to see a color change from orange to green. Okay, that's the indicator that this reaction has happened, that the dichromate has been reduced to the chromium ion. Okay. So if we have then a tertiary alcohol that has its carbon is attached to three other carbons, nothing will happen because those carbon-carbon bonds are not going to break. We're not going to replace those with the carbon-oxygen bond under these conditions. So there's no reaction and no color change. Okay? Now, what if how can we, as organic chemists, decide, well, I want to make the aldehyde versus I want to make the carboxylic acid, when the same reactant can do either one? Okay, this is where distillation comes in. So, and this is and I'm sorry, I haven't posted these slides yet. I will do that today. This is where our, this is just a kind of overall alcohol reaction. So we can have the color change from primary alcohols going to either an aldehyde or carboxylic acid. The secondary alcohol can only go to a ketone. That's the orange to green color change, and the tertiary alcohol is not going to happen. Okay. The manganate ion is another possible oxidizing agent. But I think the questions that I've seen have generally been using the dichromate ion. So how do we separate these things out? Well, we use distillation. So if we're oxidizing a primary alcohol, and we want the aldehyde, if we think about the primary alcohol and the aldehyde, who is going to have a lower boiling point between those two? Between the alcohol and the aldehyde. Gavin. The alcohol is going to have a higher or lower? Why? Okay, so yes, the alcohol has a hydrogen bonding, which is a stronger intermolecular force. What is that going to do to the boiling point? It's going to be higher. Okay? Stronger the intermolecular forces, the higher the boiling point. So the lower boiling point is going to be the aldehyde. The higher boiling point is going to be the alcohol. Okay, you knew what you were saying, you just said it backwards. It's fine. So the aldehyde is going to have the lower boiling point. So if I want to make the aldehyde and keep it, then what I'm going to do is set up a distillation apparatus like we did for the cherry Coke, where, I mean, we didn't have fractionating columns for the cherry Coke, but the idea is that the aldehyde is going to come up and vaporize at a lower temperature. When it does that, that vapor is going to come into our condenser. It's going to condense, and we're going to get the aldehyde dripping into our collection flask. The alcohol is not at its boiling point. So little to none of the alcohol is going to make it through the system into the flask. The fractionating column helps ensure that the alcohol, whatever alcohol vapors do come out, are going to make it back in, are going to drop back into the reaction flask, and that only the aldehyde is going to come out here. All right, so if we want to make the aldehyde, this is how we're going to do it. If we want to make the carboxylic acid, we have to find a way of leaving the aldehyde in the vessel. We can't have it coming out. So we can't have, an open system where the aldehyde comes out or where we're collecting the aldehyde. So instead what we do is we set up what's called a reflux condenser, which is where we put the condenser directly on top of the reaction flask. And what this does is any vapors that are coming out of the flask are going to condense right above it and drip back in. So we're going to keep the aldehyde in the reaction mixture to be fully oxidized so that by the end of the experiment, we should have carboxylic acid in our reaction flask. We shouldn't have stopped at the aldehyde. It should have, if we have enough of our oxidizing agent in the flask, then everything is going to be fully oxidized all the way to the carboxylic acid. So this is the kind of thing that organic chemists do all the time. They're trying to make a particular product. It's all about what agents are you using, what catalysts are you using, what conditions are you doing this under, are you refluxing it or not. These are all common procedural things that can drive your reaction towards the product that you're looking for. Okay, so that's oxidations of our alcohols. Another class of reactions that you need to know is esterification, so making esters. And this is essentially a dehydration synthesis reaction or condensation reaction. It's called a condensation reaction because what's happening is we've got our carboxylic acid and our alcohol, And we are essentially losing a water molecule. Okay, so we're losing, I am 90% sure that this is how it works, that we lose the hydrogen off of the carboxylic acid and the hydroxyl group off of the other chain, but I could be wrong. It could be the hydrogen and the hydroxyl group. Honestly, can't remember, but in any case, we're losing a hydrogen and an OH. Those are going to combine to make water, hence a condensation reaction where water is coming out of the reaction. Okay, what ends up happening is the oxygen of one attaches to the carbon of the other, and we have an ester. Okay. Esters are widely used as perfumes and flavorings. The cherry in your cherry Coke that you distilled out was an ester. So depending on what is on either end of that functional group determines whether it smells like bananas or cherries or something worse. Okay, but that's how we make esters, and you need to be able to show how that would happen to draw an esterification reaction or recognize one, and know that the other product is water. And that's actually, these condensation reactions are very common in biochemistry, right? Your protein synthesis, your polymerization of sugars into starch, like all of those things often involve removing a water molecule and connecting two parts together. So this is pretty common. Okay. All right. The next two sets of reactions with the halogenoalkanes and benzene follow two different, they're called substitution reactions, and there's two different types of substitution. There's nucleophilic substitution and there's electrophilic substitution. So let's talk about those two words. So the root word phil means love. So a nucleophile is something that loves or is looking for a nucleus. All right, this is something that has extra electrons. Maybe not extra. It doesn't have to be an ion. It often is an ion, but it doesn't necessarily have to be an ion. Looking for a nucleus that needs them. Something with a partial positive charge, ideally, that's looking for something that needs its extra electrons. Have extra electrons, looking for somebody who needs them. An electrophile is someone who is looking for electrons. Often something that is particularly electronegative. Okay? These two are going to find each other on Tinder and have a beautiful relationship. But the nucleophile is looking for somebody who has a partial positive charge to attack and get together with. The electrophile is looking for somebody who has extra electrons. Or is looking to, join up with something and kind of pull the electrons towards itself. So when we're talking about the halogenoalkane reactions, the substitutions tend to be nucleophilic substitutions. Okay, and what we're substituting is something else in place of the halogen. So we're substituting something that's going to replace the halogen. So this happens because the halogen carbon bonds tend to be polar bonds. Okay, the halogens are more electronegative. So what we end up with is this very attractive looking partially positive carbon. And the nucleophile is swiping through Tinder and is like, oh my God, look at that. That looks so good. I'm totally going to hit that. And it's going to come in and it's going to cause a heterolytic fission where the bonding electrons between the carbon and the halogen are going to go with the halogen, all right? So this is heterolytic fission as opposed to the homolytic fission that started the halogenoalkane reactions, right? So the bonding electrons both go with the chlorine. The carbon is left electron deficient, but luckily our hydroxide ion comes in and saves the day, and we end up with an alcohol. Okay. So the hydroxide ion is the nucleophile, and it's coming in and looking for this partially positive carbon, and it's saying, I want a piece of that, and it's going to kick out the chlorine with its associated bonding electrons. So you're going to end up with, typically when you look at these summary reaction, you would have something like sodium hydroxide coming in and replacing the hydroxide ion. It's a better nucleophile than the chlorine, so it's going to replace the chlorine. It's going to leave us with sodium chloride as one of the products, and then the alcohol. Okay, so that is a nucleophilic substitution. There are other forms of nucleophilic substitution with different nucleophiles, but this is the one that you need to know. HL students, you're going to get some more levels to this. So that is what's happening with the halogenoalkanes. The halogens are going to be replaced by a hydroxyl group to make an alcohol, or replaced by a hydroxide ion, I should say, to make alcohol. It's different it's the opposite when we come to benzene reactions. So benzene, remember, is C6H6. We often draw it as having alternating double bonds, but that's not really what's happening. What's actually happening is the p orbitals on the carbons are all kind of sharing those electrons that are delocalized and kind of creating that aromatic ring. So even though we can draw it as having alternating double bonds, these double bonds are not susceptible to attack to addition reactions the way that regular alkenes are, okay? Because that aromaticity stabilizes this structure. So we're not going to just pop in a couple hydrogens here and break this double bond, because it's not really just a double bond in isolation. It really is part of this aromatic ring. And so that stabilizes it. So we're not going to break that out. Yes? Okay, so this has to do with bond hybridization, which is not in the SL curriculum. So when you have a carbon bond that's, say, in a benzene ring, this is called a sigma bond. It's using the s orbitals, electrons in the s orbitals. And then the double bond, or this sort of aromatic ring, comes from the p orbitals. But when we talk about, it's not really exactly the p orbitals. So when we have something that's like a carbon with 4 bonding domains, we take the s and 3p orbitals, and we basically combine them and make them into 4 equivalent, up to 4 equivalent types of orbitals. They hybridize, and so you end up with sp3, or sometimes sp2, or sometimes just sp. It's complicated. So the pi is essentially like a p orbital in that it's coming out of the plane of the bond between the carbons, and so that's where the pi is coming from. Okay. Yeah, and in each of these carbons, because of this sort of partial double bond, is going to have these pi orbitals coming out, and that is what's creating these 2 donut-looking things. That's the sort of path of the electrons, the probability of where the electrons would be located. Yeah. Yeah. So what's going to happen here is we're going to get substitution of the hydrogens on the benzene. The carbon bonds are not going to break. they're too stable with that aromaticity. So we're going to end up with substitution reactions where something that's coming in, which is an electrophile, something that is electronegative or is looking for more electrons, is going to come in and say, hey, look at this juicy, electron donut that's happening over here. I really want a piece of that. I want to come in and be close to that. So I'm going to kick out this hydrogen, and I'm going to bond to the benzene ring, right? And you can make all kinds of substitutions here. Under different conditions, depending on the electrophiles, you can end up with a lot of different things coming off of this ring. I forgot to put this up as a slide, but I think I still have it here on the... yeah. So one example is a halogen. So if you take benzene and you throw it together with something like chlorine, under the right conditions, then you're going to get the chlorine is going to be the electrophile that attaches to the benzene ring, and the other chlorine atom is going to come off and be and connect to the hydrogen that was pulled off of the benzene. So you're going to end up with hydrochloric acid in this case as one of your products. Yes. Right. No, we're substituting. We're substituting. So an addition reaction would be if we were to take one of those double bonds, break it, and put like 2 hydrogens or a hydrogen and a chlorine. So the alkene addition reactions that we looked at earlier. This was a while back. The addition reactions where we're breaking the double bond and adding 2 things to the 2 carbons. So adding the hydrogenation is breaking that double bond and adding the hydrogens, turning it into an alkane, or adding 2 halogens or adding a hydrogen and a halogen. That's the addition reaction that benzene doesn't do, because that would involve breaking a double bond. Benzene doesn't really have a double bond in isolation to break. It's got the aromatic ring that's sort of self-reinforcing. All the carbons are bonded to a hydrogen? Yes. So if you break one, like every carbon basically is more like a double bond and a single bond, and the bond to the carbon. Yeah, like that. Yeah. So what we're doing is we're breaking the double bond, and then both of those carbons would be taking another one. Yeah, it would take another atom on. Yeah. So if we, for example, if we have cyclohexene that only has 1 double bond, okay, this can undergo addition, okay, because nothing is stabilizing this double bond. So if this undergoes addition, then we end up, well, here, let me use red. We end up getting rid of this double bond, and we add something. Sorry, this also has hydrogen. We add something to each of these carbons, okay, and then we no longer have the double bond. But benzene is not going to do that because they're not really double bonds in isolation. Yeah, thank you for asking for that clarification. I think that was helpful. Okay. So that is our that's our organic topic. Okay. You have a practice packet there. Again, that's going to be due next week. And I will give you a short take-home test for that as well. Probably give it to you on Friday, but, somewhat flexible due date because I know you guys are all testing crazily over the next couple weeks. But I do need to have some things in the gradebook, so that will be one of them. Okay. All right, so I'm going to pause here. I'm going to stop the recording.